అప్పుడు రాలేదంట అవి చెప్పినాయి.
వచ్చుంటే పడకుండా ఉండవు. చూద్దాంలే మనం. ఎందుకంటే నీకు మనం ఫస్ట్ పెట్టించుకొచ్చి నేను ఫెయిల్ అయింది కదా, మన రెండోసారి పెట్టిండ
రెండోసారి దాంట్లో లేదా?
రెండోసారి దాంట్లో ఫెయిల్ అయ్యారు. సరే ఎన్ని క్లాసులు పెట్టించినారు?
రెండు మూడు
మూడు క్లాసులు 3,000 చేస్తాను. చూద్దాం, దాన్ని అడ్జస్ట్ చేస్తాను.
Minimum 100.
Yes, good afternoon, all. In continuation to the previous class, today we are going to discuss about molecular rearrangement 2. In this class, we are going to discuss about some named reactions that are Hoffman rearrangement, Lawson's rearrangement, and Curtius rearrangement, Schmidt rearrangement, Beckman rearrangement, and base catalyzed rearrangement, that is benzylic acid rearrangement, Favasky rearrangement, and phrase rearrangement. Now, coming to the first, what we are going to discuss is I have given in the as per the index Hoffman, Curtius, Losses, Smith, Beckman, and electron deficient nitrogen. All these rearrangement reactions are involving electron deficient nitrogen in the migration terminus. On the other hand, the benzylic acid and Favasky rearrangements are base catalyzed reactions, which in which the carbon as the migration terminus. Freeze rearrangement reaction is an example of intermolecular rearrangement taking place by dissociation and recombination of mechanism. Then first you come into the Hoffman rearrangement reaction. The Hoffman rearrangement consists in the conversion of an amide to amide to amide. This is, suppose if you take this one is the amide, this one is amide, which is subjected to the reaction reagent. Later we will discuss what is the reagent. Now this decarbonization is, it releases carbon dioxide, then it leads to formation of amide. Right, this rearrangement is called Hoffman rearrangement reaction. What's going on in this Hoffman rearrangement? In this Hoffman rearrangement, it is treated with the amide treated with bromine in sodium hydroxide or a strong base, any strong base like potassium hydroxide, like that. Then it is turns to, this mixture is turns to BRO minus. This is the active reagent which extract the N-bromamide, that is N-bromination takes place, or N, C double bond O, N, that N-bromination takes place, that will be given. Now later, it is treated with base because this reaction is carried out in the base condition. It involves the elimination of water molecule. It is involving elimination of water molecule. Then it leads to the formation of anion of N-bromamide. Anion of N-bromamide. What is that? The proton is abstracted from here. Proton is abstracted from here. That leads to the formation of a negative charge on nitrogen. This is called N-bromamide. Anion of N-bromamide, which is subjected to a rate determining step. What's happening? It is involving a rearrangement reaction. First, it is leaving the bromine with its negative charge. Now it leads to bromide ion. Now it leads to formation of a nitrine intermediate. Nitrine intermediate. This is electron deficient intermediate, and which is, is undergoing rearrangement. That is like this. Now it leads to formation of an isocyanate. Isocyanate intermediate. Further, which is subjected to treated with water. Addition of water is taking place. Then it leads to formation of RNHCOOH. That means in that water OH is added here, hydrogen is added here. Now which is on decarboxylation. That leads to formation of amine. Okay, this is the basic mechanism of Hoffman rearrangement reaction. And this is the general mechanism. The reaction proceeds through the anion of N-bromamide. The rate determining step is the loss of bromide ion from the reaction. It leads to the formation of anion of N-bromamide to form acyl nitrine with rearrangement to form isocyanate intermediate, which is on hydrolysis that leads to the formation of carbamic acid, which is on spontaneous decarboxylation that leads to the formation of enamine. N-bromamide is it is salt containing its anion, and the isocyanate can be isolated under suitable condition. This is some doubt that the nitrogen intermediate has an independent existence. Nitrogen should react rapidly with water, used to hydroxamic acid or carbamic acid, but no hydroxamic acid have been found in the reaction mixture. Therefore, it is suggested that the departure of halide ion and the shift of migrating group in the Hoffman rearrangement are simultaneously takes place. When you consider the rate of Hoffman reaction increases when electron releasing group are present in it. Like if it is R, that R group is an electron releasing group, that Hoffman reaction rate will be increases. Next, the Hoffman reaction is an intramolecular rearrangement. No cross products were isolated. Whenever we are conducting the Hoffman rearrangement reaction between the two different substrates, that will not give four different amides. It will give only two different kinds of amines. That means that indicates that the rearrangement involved in the Hoffman reaction is intramolecular, not the intermolecular. It is the intramolecular rearrangement. and it is confirmed by the crossover experiment. Based on the crossover, here the equation is given. Based on this equation, we can conclude that this is the intramolecular rearrangement, not the intermolecular rearrangement. Now, the migration of chiral group takes place with the retention of configuration in the Hoffman rearrangement reaction. Suppose an amide which is containing with an chiral center, which is undergoing Hoffman rearrangement. During the migration, there is no change in its stereochemistry. Retention of configuration is generally observed. Okay. Next, rearrangement is loss and rearrangement reaction. Loss and rearrangement reaction we are also called it as a Lawson's reaction is carried out on the OSL derivatives of hydroxamic acid. Amines are obtained as end products on treatment of OSL hydroxamic acid with alkali. The mechanism is similar to that of Hoffman reaction isocyanates or the intermediates in the reaction. When you consider the mechanism, that reaction starts with an amide. Amide is treated with an acylation. That means OSL hydroxamic acid is generated, which is treated with base. Which is treated with base. There is a losing of one hydrogen from the nitrogen that leads to the formation of OSL hydroxamic acid anion, which is further undergoing the rearrangement that leads to the formation of an isocyanate intermediate, or which is an deacylation that leads to the formation of acyl nitrine. Acyl nitrine. This acyl nitrine further undergoing rearrangement that leads to the formation of an isocyanate. Next, this isocyanate treated with water. That water is undergoing addition on that isocyanate. That leads to the formation of carbamic acid. That carbamic acid further decarboxylation that leads to the formation of amine. Now this amine is anhydrolyzed, is generated, is the final product. Next, the reaction is facilitated by electron releasing group in R, but retarded by such substitution R. Right. It is an intramolecular rearrangement. This is also similar to the Hoffman rearrangement. It is intramolecular rearrangement. Migration of a chiral group occurs with the retention of configuration in the lossless rearrangement. Next, ఇది కాదు బ్లూ స్కెచ్ తో ఉంటుంది చూడు బ్లూ స్కెచ్ తో రాసి ఫస్ట్ పేపర్ ఐ థింక్ బ్లూ స్కెచ్ బ్లూయిష్ వైలెట్ ఉంటుంది చూడు స్కెచ్ Right. Now coming to Curtius rearrangement reaction. This is also very similar. We need to convert this acyl chloride or an acid hydroxides into amines. In this, we are going to conduct this reaction in two ways. If you take the acid chloride, which is treated with the sodium azide, NaNO3, NaN3, that sodium azide. That sodium azide uh, is is reacting with the acid chloride that leads to the formation of an acyl azide. This acyl azide on heating that leads to the formation of amine. Once the formation of acyl azide, it is undergoing the reaction. That means whenever we are heating, it is it is involving the removal of nitrogen gas that leads to the formation of acyl nitrene. Acyl nitrene. This acyl nitrene is converting into corresponding isocyanate, corresponding as isocyanate. Or this acyl azide, it is also generated from the acid hydrazide, which is treated with HNO2 nitrous acid that leads to the formation of an acyl azide that leads to the formation of this intermediate. Now, this is undergoing rearrangement of that R group, whatever the substrate is there, that is undergoing rearrangement. That leads to the formation of an isocyanate by the elimination of nitrogen gas. Now, after formation of isocyanate, we are adding water that leads to the formation of carbamic acid. That carbamic acid undergoing decarboxylation that leads to the formation of amines. These are more or less similar to Hoffman rearrangement. Once in these three reactions, what are that? Lawson's, Hoffman, Cutters. In all these three reactions are involving the same intermediate, that is isocyanate. That isocyanate leads to the formation of amine. Right. Next, Smith rearrangement reaction. The Smith reaction is actually a group of reactions in which hydroxoic acid in sulfuric acid is used as the reagent. This reagent react with the carboxylic acid and carbonyl compound to give the amines and amides respectively. Smith reaction with carboxylic acid. The reaction is modification of the Curtius reaction. In this reaction, an acyl azide is formed with in with which is converted into an amine containing one carbon less through an isocyanate. Isocyanate is not stable intermediate to from the which is formed from the reaction mixture or during the formation of continuation of the reaction. The reaction may be assigned the following mechanism. This carboxylic acid. This carboxylic acid, which is treated with hydroxoic acid in an acidic medium, that leads to formation of amine. During this reaction, what is the pathway it is choosing? That the whatever the proton is given by the strong acid, that is protonation of that carbonyl group of the acid that leads to formation of a carbocation, which is attached with two OH groups, which is reacting with the hydroxoic acid that leads to the formation of this intermediate, which is for other reacting with the acid that leads to the formation, that leads to involving in the elimination of the water molecule. Then it leads to the formation of this product, which is on removal of slow nitrogen that leads to the formation of isocyanate. This isocyanate on addition of water that leads to the formation of carbamic acid. This carbamic acid undergoing decarboxylation that leads to the formation of amines. Okay, this electron releasing group in R increases the rate of reaction. The reaction is intramolecular reaction. As with the other rearrangement, the migration group in the Smith reaction shift with retention of configuration. Uh, Next, Smith reaction with ketones. This ketone is reacting with hydroxylic acid in acidic medium that leads to the formation of an amide. An analogy: the reaction of carboxylic acid with the hydroxylic acid. The following mechanism is proposed for the reaction. This ketone, which is on reaction with, which is on protonation with the proton, which is given by a strong acid, that leads to the formation of protonated ketone. Then it is reacting with the hydroxylic acid. Further, it is rearranging, it leads to the formation of acyl nitrite, which is further involving elimination of nitrogen gas that leads to the formation of isocyanate. This isocyanate further aldehyde generally it's the N-alkyl formamide. N-alkyl formamide. This formamide is generated in this Smith reaction with the ketone. Now, this is the carboxylic acid. This is the aldehyde, which is reacting with the hydroxylic acid that leads to the formation of cyanide, and along with the uh, N-alkyl formamide is the product. Similarly, if we take ketone, the ketone leads to the formation of this kind of intermediate that is further undergoing rearrangement, it leads to the formation of N-alkyl amide. N-alkyl amide is generated. Next, Beckmann rearrangement. This is the acid catalyzed rearrangement. Generally, carbon and compounds on treating with the hydroxylamine hydrogen chloride that leads to the formation of an oxide. That oxide is undergoing rearrangement in the presence of acidic medium, especially Lewis acid, that leads to the formation of amides. For example, here the benzophenone is treating with the oxide hydroxylamine hydrogen chloride that leads to the formation of benzophenone oxide. This benzophenone oxide on acid catalyst that leads to the formation of benzanylide. This rearrangement could be a near direct interchange of the pH and OH. Whatever the group opposite to the OH group, that is undergoing the rearrangement. Now here the pH is opposite to the OH group, that is undergoing rearrangement, that leads to the formation of N-amide. Right. If we take other products, the Beckmann rearrangement of ketoxime is highly specific in that it is always the anti-group in the oxime that migrates. The exclusive migration of the anti-group has been confirmed in the rearrangement of isometric 2-chloro-5-nitro benzophenone oxime. Right here, Z isomer of the oxime, this is the E isomer of oxime. In the both the case, the 2-chloro-5-nitro-benzophenone is taken for the preparation of an oxime, which is further after formation of the two isomers, which is further treated with the acids. If it in the case of cold alkali, it is undergoing the cyclization that leads to the formation of 3-phenyl 5-nitro benzoisoxazole. But this kind of product is not observed in the E isomer because the OH group and this chlorine in the phenyl group are far away or anti to each other. Due to that reason, that cyclization is not takes place in the case of A isomer, but Z isomer it is easily takes place because the OH group and the Cl group are both are near to each other. Next, rearrangement. How this rearrangement is takes place. Whenever we are taking the oxygen, which is treated with acid, a protonation is takes place on the OH group that is slowly detached from the oxygen that leads to the formation of nitrinium ion. Nitrinium ion by the removal of water, it is the slow step and rate determining step. After that, it is rapidly undergoing the rearranging of alkyl group, that whatever the group anti to the OH group, it is undergoing the rearrangement. Then it leads to the formation of this imine derivative. This imine derivative further on addition of water that leads to the formation of hydroxyimine. This hydroxyimine undergoing the tautomerism that leads to the formation of N-substituted amide. This is the major product. Next, other reactions, base catalyzed rearrangement reactions. In base catalytic rearrangement reaction, first an electron surplus migration origin is created, which leads to the nucleophilic shift in subsequent stages. The benzylic acid rearrangement and the Pavlovsky rearrangement are two examples of base catalytic rearrangements. Benzylic acid rearrangements. This is the benzylic acid which is treated with the OH group. Then it is OH addition is takes place when you come into the reaction mechanism. This is the past step, right? This is treated with the OH. The OH is attacking on one carbonyl group. Simultaneously, addition of OH group is takes place on the carbonyl group. That again it is rearranged. During the rearrangement, the phenyl group is migrating from its migration origin to migration carbonyl by the polarization of this pi bond on the carbonyl group in the slow state. Okay, this migration takes place in the slow state. After that, the OH hydrogen is shifted to from COOH to OH, O minus. That leads to the formation of a benzylic acid salt is generated. On neutralization, it leads to the formation of benzylic acid. Similar kind of rearrangement can be seen in several esters formation. That is the benzoin is treated with the alkoxide group that leads to the formation of benzylic acid ester. Similarly, it is treated with the MgX. Now this cyclic intermediate is generated. Later, this kind of product is generated. And hydroxyketone product is generated. Next, Pavlovsky reaction. In the Pavlovsky rearrangement, an alpha haloketone is transferred to an ester using an alkoxide or to a catalytic salt using a hydroxide. Now, in this case, uh, 1, 2, 3. 3-phenyl 1-chloroacetone is treated with the base that leads to the formation of a rearranged product that is 3-methyl 3-phenyl propionic acid. 3-phenyl propionic acid. In 2-chlorocyclohexanone is treated with this ethoxide ion, sodium ethoxide or potassium ethoxide, that leads to the formation of ethyl cyclopentoate acid. Acid ester is generated. Now, in this case, if you find the first reaction case, how this rearranged product is generated, that can be explained the following. It is treated with base. It is treated with base. A proton is grabbed or absorbed by the OH group that leads to the formation of carbon ion. This carbon ion negative charge is donated to the alpha electron deficient carbon, simultaneously removal of chlorine. A 3-membered cyclic intermediate is generated. This is a cyclopropanone intermediate is generated, which is further reacting with OH minus base that leads to the formation that is undergoing the addition of the carbonyl group C double bond O. Then O minus intermediate is generated. Further, the dissociation or cleavage of rings takes place that leads to the formation of a resonance stabilized carbon ion is generated, which is further neutralized with the proton neutralization that leads to the formation of carboxylic acid. The rearrangement of 2-chlorocyclohexanone labeled with C14 at the chlorinated carbon supports the mechanism. Now, this is the 2-chlorocyclohexanone, which is treated with the sodium ethoxide. Then it leads to the formation of carbon ion. This negative charged statics is negative charged electrons are donated to the alpha carbon of cyclohexanone. Then it leads to the formation of cyclopropanone derivative, which is further reacting with oxide on addition of ketone group that leads to the formation of this ester. We have given some example. Now coming to the freeze rearrangement reaction. This freeze rearrangement reaction, when an aryl ester is treated with the anhydrous aluminum chloride, the acyl group it migrates to the available ortho and para positions in the aromatic ring. This reaction is known as the freeze-rearrangement reaction. For example, metacrysyl acetate. Metacrysyl acetate is treated with aluminum chloride. It leads to the formation of para-acyl cresol and ortho-acyl cresol. At lower temperature, para-isomer is the major product, whereas the higher temperature, the major product is ortho-isomer. The ortho-isomer is more stable than the para-isomer. Para-isomer is converted into the ortho-isomer on heating with aluminum chloride. Now, this freeze rearrangement is intermolecular rearrangement reaction. For example, you take the toluene. Yes, paracrysal, paracrysal and 2-chloro-paracrysal, crysal acetate derivatives, which is treated with AlCl3, that leads to the formation of ortho-acyl 2-chloro 5-chloro cresol, paracrysal, that are the two are the unusual products. The crossover products, usual products are 2-acyl 5-chloro paracrysal, and another product is 2-benzoyl paracrysal, and the crossover products are different. 2-benzyl 5-chloro paracrysal and 2-acyl paracrysal. These are the cross products, right? Isolation of the cross product suggests that the following two-step mechanism. What is that? Paracrysal, which is treated with the aluminum chloride, that leads to the formation of aluminum uh, aluminum complex, which is undergoing the acylation at ortho position, that leads to the formation of a 6-membered aluminum cyclic intermediate. In this is responsible for the formation of other substituted product. Now, in the crossover experiment, there is a complete detachment of this acyl group and benzyl group from the acetate uh, starting material. Therefore, after in the middle of the reaction, that acetate ion and the benzoate ion are reacting with the in the equal portions with the other cresol substrates. That is the formation of cross products. Okay, this is about the rearrangement reactions. Okay, next tomorrow we'll continue with the elimination reactions. Thank you.